Okay, so I'm going to teach you partial fractions and logistic differential equations. Let's start with a multiple choice of partial fractions from 2008 BC exam, question number 19. So here's our answer choices. So first thing we're going to do is we're going to separate the denominator into a over 2x minus 3 plus b over x plus 2 equals 7x over 2x minus 3 times x plus 2. Then we're going to multiply the denominators by each other so that we can get a common, or we're going to multiply the bottom times the top so we can get a common denominator. So we have a over, or a times x plus 2 plus b times 2x minus 3 equals 7x. Next, we're going to plug in values for x that would make one of the letters equal 0, either a or b. Let's start with b. So if we plug in 3 halves for x, b will get multiplied by 0, which makes the b cancel out. However, we still have 7 halves a equals 21, which leaves a to equal 3. And then we're going to do the same with solving for b, so we're going to plug in something that would make a cancel out, and that would be -2. And if we plug in -2 for all the x's, we get -7b equals -14. So b equals 2. And then, so then we have the integral of 3 over 2x minus 3 plus 2 over x plus 2 dx equals the integral of 7x over 2x minus 3 times x plus 2. So here's where it gets a little tricky. We know that the integral of 1 over, or dx over x is ln of x, because the derivative of ln of x is dx over x. So we're just going to do integration of this and integration of that with the 3 on the outside. So it's going to be 3 halves natural log 2x minus 3, and it's not just 3, it's 3 halves because you have to take the derivative of what's on the inside and bring it out too by some method of u substitution. I don't want to get into that. And then we have 2 ln of x plus 2, and don't forget your constant, and that means that our answer choice is A. Okay, so next let's do a question over logistics, since I know a lot of us are kind of shaky on that. Okay. So it says, which of the following statements characterizes the logistic growth of a population whose limiting value is L? Let's just go through each of these bullets and prove them true or false. Okay, so number 1, the rate of growth increases at first. Well, first let's look at a graph of a logistic curve. See that? Okay. So there's what that looks like. Logistic curve, we've seen it all before, it's S-curve. So since our limiting value is L, this is our horizontal asymptote, and it's going to be L. And it says the rate of growth increases at first. Well, basically it's telling you, does the slope increase at first? And looking at this, we can see that, yes, it does increase at first. So we can say this one is true. Number 2, the growth rate attains the maximum value when the population equals L over 2. Number 2 is true because it's basically asking when the growth rate attains a maximum value. Well, when you're asking when the growth rate attains a maximum is when also asking when the logistic curve has a change in concavity or a point of inflection. Since the carrying capacity is L, it's always going to be at L over 2, which is this. So that means number 2 is true. The growth rate approaches 0 as the population approaches L. Growth rate means slope, so that means the slope is starting to become horizontal as the population approaches L. And as we can see here, that's true. Not only do we see it by the model, it's because L is a horizontal asymptote, so it's approaching, like it's starting to flatten out, like as we can see right here. So number 3 is true too. Since they're all true, that makes our answer choice E. Okay. So next, one more question. We'll do a free response over logistic curves. Okay. A population is modeled by a function p that satisfies the logistic differential equation seen here. A. If p of 0 equals 3, then what is the limit of p of t as t approaches infinity? If p of 0 equals 20, what is the limit of p of t as t approaches infinity? Okay. So on A, the first question, when p of 0 equals 3, the limit of p of t as t approaches infinity is 12, because 12 is the carrying capacity. So basically, if we were looking at like a logistic curve of what we saw in the previous question, it's asking what the horizontal asymptote is, and it doesn't matter what p of 0 equals. The limit is always going to be, or a limit as t approaches infinity of p of t is always going to equal 12, because 12 is the carrying capacity. Which answers our next question too, because it tells us a different scenario, or it gives us a different y value of 0, but the limit is still the same, because 12 is the carrying capacity, which is seen by this. Since the only other equation, or the equation for logistic, looks like this. And this is the carrying capacity. So that's why this is the carrying capacity, because 1 times 12 is 12. Okay. B. If p of 0 equals 3, for what value is the population growing the fastest? So basically, just like the last question, it's looking for a maximum, which occurs at the halfway of the carrying capacity. And since we established in part A that 12 is the carrying capacity, we just take half of that, and that is 6. So the 6 is when it has a change in concavity, so it's also the maximum of, or when the population is growing the fastest. Okay, part C. A different population is modeled by a function y that satisfies the separable differential equation. Find y of t if y of 0 equals 3. So they just gave us an initial condition, as we can see right here. So we're going to differentiate first, separate variables, and don't forget you can only separate variables by multiplying or dividing. So when we separate variables, this is what it looks like, and we're just gonna clean it up by distributing right here. And then that's how I got this. And then you're gonna integrate both sides. So you get natural log of y equals t over 5 minus t squared over minus 120 plus c. Then you're going to plug in the initial condition that they gave us up here. And then you're going to get natural log of 3 equals 0 over 5 minus 0 squared over 120 plus c. So c is going to be the natural log of 3. You're going to plug c back into the equation. Then you're going to solve for y by taking the inverse of ln, which is e. So you're going to take e of everything. And since e of natural log of 3 is 3 and it's adding, you're going to multiply 3 times e to the t minus, or e to the t over 5 minus t squared over 120. And then part D is asking for the function y found in part C, what is the limit as t approaches infinity of y of t. And our equation was this: y equals 3 t over 5 minus t squared over 120. So the answer of D is the limit of t approaches infinity of y of t equals 0. Okay? So that is it for partial fractions and logistic equations. Hope you learned a lot.